recording here. All right. So, pretty exciting day yesterday. I figured out how to ditch the tables.
That's exciting.
Yeah, I know, right? Not that I didn't know how to, I just didn't want to force you to use R or anything like that during a quiz or a final exam. So what I did was I found a plugin that is a probability calculator, and I posted the link in the general course material and resources, which is up at the top. So let's see here. I'll just snap this. Let's see here. Boy, you start a new page. I had all this time and I was just yapping. That's par for the course though. Let's see here. There. Okay. So I found this pretty fun probability calculator. Oh my gosh. Crop there. Oh, and I do want to say just to those on Zoom, because I know there's quite a few of you on Zoom. Wow, lots of you. I will not be able to see the chat. So if you have something to say to me, you have to say it to my ears using your voice. Okay. Not to my face. No. Okay. And so this probability calculator is this kind of fun plugin, not without some glitches, obviously. What's a new thing? Without some glitches, but I'll show you the workarounds. So yesterday, I found a plugin that helps us calculate p-values. Oops, plural. Here. So there is a link on our Moodle page, but it's also included in the assignment that I have not posted yet because you don't know what to do yet, and that would be weird for me to post. But it will be in there just to show you, because it's hidden right now. Assignment 14 is for one sample mean. Like I said, you can't see it because we're going to take this week to talk about 7.1, and then this is the assignment for 7.1. But
49 points.
Just don't worry about that, okay? Just don't don't worry about that. Pay it no mind. All right, let's see here. So what it's going to look like is inside the assignment. Wait. You'll have this plugin. I know it's kind of showing up weird. So I just want to show you how to use this, okay, instead of the tables. It's going to be able to give us better p-values and critical values than the tables ever could. All right, so we're finally moving away from it. It's very exciting. All right, now I'll grab it from the link. Probability calculator. This is where it starts off. Okay. And what I find is that I have to kind of click down at the bottom, just kind of click around for it to show up. So for example, if I do, it does this thing where it doesn't want to show me what I want it to show me. Yeah. So often it shows up like this, where there's nothing at the bottom. Okay. So then I have to kind of click around at the bottom. And if I click around here, then it shows up with values that I can change, which is pretty weird. So like I said, not without some glitches. I suspect it's a mobile thing because I'm on my iPad, but because on my desktop it's showing up fine and there's enough room and stuff, but yeah, just kind of annoying. But if you click around, it should show up and it should show that probability of X being between -1 and 1 is 0.6827. Does that check out with what we know already? Yes, right? The 689599.7 rule says that between the first or within one standard deviation of the mean, the area should be about 68%, or more precisely 68.27%. Right? So that all checks out with what we know. So let me just bring that in here. So like I said, not without some glitches, but it's better than nothing. Especially for today, we're gonna introduce what would be a new table or a new distribution. So I'm gonna just use this. I'll use the t-table just to illustrate the connection. You'll have access to the t-table and the z-table and the chi-squared table during the quiz and the final exam, but you'll also have access to this. So it's up to you. As the UBC saying goes, to a mest, it's yours. All right. Being a UBC alum and all, to a mest. All right. So let's see here. One of the things that I was finding was, unless there's an underline, I can't seem to change the value. So for example, I can't seem to force the area to be 0.95, for example, in the center. That's weird, but there's a workaround, always a workaround. But let's see here. This is the area between Z equal to -1 and Z equal to 1. Because that's what I told it. And just to zoom in on these options here, copy. Right, depending on what I want to find. This is the area to the left. This is between, and this is the area in both of the tails. And this is the area to the right. And changing those would let you adjust which area it's finding. This is for the normal distribution. The normal is the Z curve. And Z with a mean of 0 and a standard deviation of 1, that is Z. Right, with a little bit of practice using this plugin, right? I don't want to call it an app or an applet, although it probably is an applet. But anyways, once you kind of practice a little bit, you'll be able to change the mean and the standard deviation to be from the question, right? And then you would use the Z value, or sorry, the X value from the question, which means you don't have to calculate the Z anymore. But a lot of the questions that we're doing ask you to give Z as one of your answers. And so you may as well calculate it and just use the standard normal. But so pretty fun, right? If you wanted to replicate the Z table, what would you do? You would change it to the area to the left. And if we just want to pick a value that we know, right, what's an easy one? 1 point, well, that one's rounded. Let's do a Z of 0. What do we think, or what do we know the area to the left of Z of 0 is? If it would do anything. Uh-oh. What if I broke it? Refresh. Is it my internet? Perhaps. Hardwired in. Okay. Okay. Come on. It's a simple calculation. Hopefully my Zoom stays on. Okay. Usually when I do weird stuff with changing between Wi-Fi and hardwired, it doesn't like that. Come on. Maybe it's because I have my RStudio Cloud open. Let's close some tabs here. It's completely hung up. I'm not on the screenshot or anything. That has happened. No, it doesn't want to do anything. Most of today's class is me showing you how to use this thing. So, so there's that. Okay. Go. Okay, fine. Fine. I'll try the link. Start fresh. Okay. I want the area to the left of, let's do something crazy, of Z equal to 0. The area to the left is 0.5. That confirms it. We could check our, now I'm scared to leave that page. Don't be scared. It's supposed to work. Let's go to our trusty table. Let's do this one. Negative 1.65. We know should return an area to the left of 0.0495. Negative 1.65, which I feel like is what you said. It's our go-to. Is 0.0495. So it's confirmed. So this matches. And let's see if I can keep this. Okay. The Z table gives the area to the left. So to replicate it, use this button. Should have copied and pasted, but I'm holding onto my screenshot in my paste. There. Maybe I'll do this. There. And then this matches. I know it's tiny, but I'm keeping it all on the same page. Matches the Z table. Whee! Which means we don't need it anymore. Like I said, you'll have it if you want it, because that's how I introduced it. I am just blowing things up more than halfway through the term, but it feels good. Feels good. So when we talk about the Z table or the normal distribution, right, that's the Z distribution. So if we go back to this thing that's hopefully working still, you'll be able to change between different distributions. That's cool. We've only seen a small number of these distributions, right? But we've seen the chi-squared distribution just on this quiz, right? As we saw the chi-squared distribution. There are a couple of things to keep in mind, right? We still need the degrees of freedom. So you would change that here. Let's say I have 3 degrees of freedom, right? The degrees of freedom changes the shape of the chi-squared distribution. It makes it more skewed with lower degrees of freedom, and it kind of approaches a somewhat normal distribution as you increase the degrees of freedom. Another thing was that for chi-squared distributions, we were using the critical value approach because it was easier with the table, but now it'll be easier to find the p-value. Okay, and the p-value is always going to be the area in the tail for a chi-squared, one tail. Okay, and just as before, if you kind of click around down at the bottom there, you can put in your chi-squared value. Okay. Let's say the chi-squared that you calculated is 12.3. Oh my gosh. There. Then the p-value is going to be 0.0064, for example. But wait, there's more. Don't delay. Purchase this ShamWow. There. Okay. Gonna bring this in to talk about. Okay. I should have used one that had a chi-squared value. Should have picked a chi-squared that's on this scale. Now it just looks empty. Okay, let me try that again. How about 9.7? That's a good number. Turns out, well, studies show that humans are really bad at making up numbers. That's been proven. Random numbers. And you'll see that in action in just a bit here, when I have to make up a bunch of random numbers. Which means, and it's pretty interesting because that means that it's easy to figure out what random numbers were generated by a human. And so it's someone's theorem. It was someone's theorem, and it was to catch fraudulent checks, because the check account numbers were all weird. They weren't truly random. We favor things like 9s and 1s. Anyways, it's pretty fun theory, but anyways, back to reality. What happened? Nothing but glitches today. It's a joke in there somewhere. We change it to a chi-square distribution, right? We would set this. It's doing that thing when it doesn't show up down here. When information is missing, click around the bottom area. It could just be like a cell phone, iPad thing going on. But if I click down there, hey, fine. I just found this yesterday, so I'm allowed to have little hiccups, I think. Or maybe I give myself too much wiggle room. But it was still very exciting. There. Okay, so then this should show up, and it says that the p-value for a calculated chi-squared of 9.7 is 0.0213. What I could do is I could change this area. I could force it to be the alpha level, right? And then to see what the chi-squared critical value is, right? So we can still find the critical value. This gives the p-value, but forcing the area to be the alpha level. I hope it does it. Lets me do it. Hey, why am I writing out alpha? It's like I'm typing. The alpha level will give the critical value. Okay, so let's see if it'll let me do that. So if I force this to be 0.05 at 3 degrees of freedom, the critical value is 7.8147. Let me bring that in. I want to make it, oh my gosh. So now if I go to my chi-squared table and I look at 3 degrees of freedom, and I force this area to be 0.05, right? 7.8147 is just a more precise critical value. They don't match, but they quote match. Right, one's more precise. Okay. So you can use it to find the critical value if that's the approach that you like. Okay, I've gone way off script, but I also want to make sure I don't forget anything. All right. Let me just check here. Ha. Let's say to calculate chi-square critical values, and I made that mistake this morning too. To calculate critical values for confidence intervals, there's a workaround. Okay. And so to calculate critical values for confidence intervals for proportions, because we're going to introduce a new distribution today. Okay. We use the area to the left, which is going to be the tail. So I find that the easiest way to do it is to just use the area in the lower tail. Yeah. So we find the Z that has the appropriate area in the tail. Okay. So for example, I'll put it on a fresh page here. If I need to find a 99% confidence interval that looks like this, right? I want to find the negative Z star, which of course by symmetry is going to be reflected in a positive Z star. I want to find this Z star, right? For my confidence interval for proportions, which means that, okay, if I have 0.99 in the middle, it means I have 0.01 left in the tails. So then here I have 0.01 divided by 2, which is 0.005. And then by symmetry, this area must be 0.005. A couple of ways that you could do it, right? You could find the area to the left and force it to be 0.995, right? The total area to the left. I like to use the negative just because it's a little bit cleaner. I don't have to add these two in my mind, right? But then I'd have to drop the negative on the Z. So it's kind of choose your poison, right? So if I'm finding a critical value for a confidence interval for proportions, that means I need a Z table or a Z distribution, the normal distribution. I'm going to force the area to the left to be, and this is where I click around here, there. I'm going to force it to be 0.005, which gives me, wonder if I can, I don't dare mess with it, so I'm just going to screenshot that. So then if I close it, yeah, of course it doesn't show up. That's okay, I guess. So here I've forced this area to be 0.005, which means that my Z star or my negative Z star is negative 2.5758, which means that Z star itself is going to be 2.5758. Nice. Doesn't really matter. You could keep the negative, but then when you add a negative, it's subtraction. And then if you subtract a negative, it's the addition, and it makes it kind of weird. So I would just drop the negative. But we can confirm this using the table that we used before, which was the T table. We can confirm this using the t-table. Right, I picked a value that I knew was going to be in the table. 99% confidence interval, has a Z star of 2.576, which is basically the same as 2.5758. Ta-da! Okay. Now here's where I have to say that I'm sorry. I didn't know about this earlier. Made you do a bunch of calculations by hand. Don't worry, you won't have to do that, I guess, anymore. Although, might be nice. Yeah. If you go to the statistics tab instead, so we've been working in the distribution tab here. If you go to the statistics tab, then there are a bunch of options. If you scroll down to the very bottom, there's a goodness of fit test, for example. You would tell it how many rows you need. So for our quiz, I think there were 4 rows, right? You would put in the observed count. Let's say this is where I have to come up with a bunch of random numbers, 14, 18, 21, and 32. And then you do have to find the expected counts on your own, and that's from the question, right? But if I have 85 divided by 4, is that a nice number? Who knows, right? Feels like not really, but. $21.25 for all of these. Let's just say I'm testing if the uniform distribution applies. So you'd have to find your expected counts and then plug them in. And this is where it is a little bit annoying because it does calculate the chi-squared value, but it doesn't show it. So, and I guess I didn't figure out if I change the number of rows, it clears it and then it makes room. So it is a little bit weird and glitchy. The way I tested it inside the assignment and for the final exam, there should be enough room. But if there ever isn't, then just let me know and I'll change it's just in the browser. I don't know what's going on. But here it gives the degrees of freedom, of course. It gives the chi-squared that you would have calculated, save you so much work, and the p-value. Wow. That's worth getting to know. All right. There is one chi-squared question on the final exam. And if you want to use that built-in tool, go ahead. It's totally fine. So here, so now I'm in the statistics tab. We can conduct hypothesis tests. You would fill in these numbers. So for a goodness of fit test, fill in these columns from the question. And then these are returned. Right, this being your calculated chi-squared, and this being the p-value. That's nice. There's even the chi-squared test, just the general chi-squared test is going to do a test of independence. And so, and this is where I really need to make up numbers. 17, I always do 17, 21, 34, 25. I don't know, I'm just making stuff up to fill the table so that we can see it. 12 and let's say 15. Or 5, I guess. In this kind of option, I guess, we have the option of finding or it telling us the expected counts, okay, for each of the cells. How does it know that? Because it's just a formula, right? If I've entered this two-way table, then it's the row total times the column total over the grand total. It has all that information, so it's able to do the calculation for you. Okay, so oh, well, that's kind of fluky, but we saw 17 and we expected 21. We saw 21, we expected 17 to switch around those, I guess. 34, we saw 34, we expected 32.6, et cetera, et cetera. So it has those expected values. And then if I check off the chi-squared contribution, it tells you what each cell is contributing. And then the chi-squared itself would be the sum of all those values. Now, this is where it gets annoying because it cuts off down here at the bottom. And I cannot figure out how to make it make sense. Okay, so this is a chi-squared test of independence. And here, I can't scroll down. And definitely play around with it and make sure it matches up with, I opened up quiz 3 and the other ones should be open too, but I'll just have to double check so that you can go back and you can review it and use it for practice and just kind of check your answers. But I can't scroll down. So to see these values, the way I can only seem to do it is to uncheck the expected count and the chi-squared distribution, uncheck expected and chi-squared contribution, and change the number of rows or the number of columns. This clears the table. Like I said, there are glitches. Boy, I'm gonna rewrite that. Not that much better, but whatever. Wait, wrong. Okay, so I'm gonna uncheck the expected count, chi-squared contribution, and that brings things up and hopefully this works. If I change the number of rows to 2, Is that better than just doing it by hand? I'm not so sure. I feel like I'll do a lot to not have to do hand calculations. There. That's weird, but. So then this is the calculated chi-squared, and this is your p-value for that. With 2 degrees of freedom, I guess I drew over it. Okay. So play around with this tab. Because I think you might find it helpful. It also does a hypothesis test for 1 sample proportion, 2 sample proportions. Gets a little bit weird because there's a lot of options. Okay, the first chunk is mostly for means, gives you the option between a z-test and a t-test. We're never going to do a z-test for a mean, and I'll kind of whine about why not, but whatever. But then the z-test of a proportion or the difference of proportions, right? And then we have the chi-squareds down at the bottom. The estimates are going to give you the confidence intervals. So if you want to do a z-test of a proportion is just 1 proportion, I want to see how far is this sample proportion from 0.5. What is it? For example, there. I choose my alternative hypothesis. It's not equal to. I have 32 successes in a sample size. Notice how it's just asking for the information that we would need to solve the problem anyways. There. N is 68. It tells us what the calculated Z is. Right, 32 over 68 is pretty close to 0.5, which is what the Z score is telling us, right? But it also gives us the p-value. In fact, it's the 2-sided p-value, right, of 0.6276, which is massive because it's so close. Yeah. So you can play around with that, see if it saves you any time. Definitely for the chi-squared, it'll just might save you some time. Yeah. Okay. Like I said, I kind of went way off script here. It's just too exciting, you know? Okay. Wow, I ripped ahead too. Okay. This probability calculator will be available in all of the assignments and the quizzes, as well as the final exam. Okay, so if you learn how to use it and you like using it, then that is great. And at one point yesterday, it's easy to get caught up in, well, this just does the chi-squared calculation for them. That's cheating. I was like, no, that's not cheating. That's just saving some time. You still have to know how to use it, right? And so I still feel fine about it. So this probability calculator will be available in all assignments, quizzes. I guess at this point, quiz number 4 and the final exam. So it's going to be a matter of kind of getting comfortable with it, learning how to use it, learn your way around it. And then we can finally move away from these tables. How about that? Okay. Chapter 7 today, big day. And like I said, I will be using just the probability calculator. I'll show you just briefly the t-table, but on assignments and the quiz and the final exam, you'll have to use the probability calculator for any means questions. So chapter 7 is inference for numerical data. Numerical means that we're going to be analyzing the mean, which is the average. And I know I said that way back at the beginning of the term, and I'm sure you kind of said, sure. And then we forged ahead. But comparing it to chapter 6, which is inference for categorical data, we are doing the same thing as we were. We are going to find confidence intervals. We are going to do hypothesis testing. But for categorical data, we were testing the proportion, right? Either one sample proportion, or how do two proportions compare to each other? What if I have multiple proportions? That's a chi-squared test, right? And so we were learning the ropes using proportions. Now we're going to apply that same technique, but to analyzing the means. Okay. So we're going to start in 7.1, which is one sample means with the t-distribution. The t-distribution is very similar to the z-distribution. So it's very similar to the z-distribution, with a few quirks. Okay. The main thing is that, and at this point, we're kind of used to seeing it, right? The chi-square distribution changes shape depending on the degrees of freedom. And the same thing is going to happen with the t-distribution, right? And it will also rely on the degrees of freedom. So just as the chi-squared distribution changes with the degrees of freedom, the t-distribution also changes with the degrees of freedom. Also changes with the degrees of freedom. It's not going to be as drastic as the chi-squared. It's going to look something like this. Oh. I will say them using different shades of blue might not be the best thing. but kind of the strongest line is the normal distribution. So that's going to be our Z curve. Z is the standard normal distribution. Okay. Now, the T distribution with 8 degrees of freedom is going to be the line that's the closest to the normal distribution. Okay, so it's quite high up here, right? And so it's just got a little bit of a shorter peak, I guess, which means, well, as we decrease the peak, right? If you kind of think of it like this, right? If I decrease my peak, then I have to make room in the tails. Okay. And so that's what the T distribution does, is depending on the degrees of freedom, it's going to make more room in the tails for smaller degrees of freedom. Room in the tails is equivalent to probabilities of extreme things happening, right? And so here, right, the normal distribution comes down pretty tight onto the axes almost immediately, right? Whereas 8 degrees of freedom, for example, is just lifted up a little bit more. And then I think it's 1 degree of freedom here has kind of the most room in the tails. So how do we find these degrees of freedom? For one sample mean questions, it's going to be your sample size minus 1. So the degrees of freedom is going to be n minus 1 for one sample mean questions. It's one of those things that I will tell you how to find the degrees of freedom, just like I did for chi-squared on the formula sheet. Right? And so it's going to be your sample size minus 1, which means what? To have a degree of freedom of 1 is pretty weird. Means you have a sample size of 2. Analyzing the average of 2 things is not going to get you very far. So of course, the average of those 2 is volatile. And so we need to make room in the tails because we don't know what's extreme. Right? So here, like I said, as the degrees of freedom increases, which means that n is increasing, right? If the degrees of freedom is just trailing behind by 1, right? What I'm really saying is n increases. So as your sample size increases, the area in the tail becomes smaller, okay? Or becomes closer to the area in the tail for a Z. So as the degrees of freedom increases, the area in the tails gets smaller. Kind of the reverse of that is for small degrees of freedom. Even looking at, 8 degrees of freedom, 8 degrees of freedom is still pretty close to what we're used to seeing, right? So that's a sample size of 9. So we don't need a huge, huge sample size, but for very, very small degrees of freedom, so kind of definitely less than, I'll say 20, just as a guide. Okay. Maybe I'll even say 10 here. Less than 10. Okay. So pretty small. Okay. The area in the tails is thicker, or maybe it's wider, I don't know. Which means the probability of extreme values is higher. Which is really just a reflection of your estimate. So your sample mean is not as robust as it would be if you had a larger sample. Right? And I'm not going to make you get into that, but we'll save it for 240. How about that? Maybe I'll bring this in over here. Here. You might remember the central limit theorem for proportions. It's what allowed us to say that, okay, then I can follow a normal distribution centered on P with a standard error of the square root of PQ over N, for example, right? So we're gonna have that same scenario, but for the sample mean. So the central limit theorem is not really something that we worry about. We examine it better in STAT 240. For us, it's just a tool that we use. And so when we collect a sufficiently large sample of n independent observations, that's kind of a loaded way of outlining the conditions that we need to check. So this is really going to be the conditions that we need to check. And I'm going to talk more about those, so we'll parking lot those. But independent observations from a population with mean mu and a standard deviation of sigma, right? Those are the population mean and standard deviation. The sampling distribution of X bar will be nearly normal, right? So nearly normal with a mean mu and a standard error of sigma over root n. Yeah. Just a reminder that X bar is the sample mean. So what this looks like is that X bar is approximately normal, centered on mu with a standard error of sigma over root n. The problem that we had with proportions is the same one that's haunting us now. Well, I don't know mu and I don't know sigma because I don't have the population. I only have a sample, right? And so now what? Instead of mu, we're going to center this on the hypothesized mean, typically. And so in practice, we center on the hypothesized mean and that's for hypothesis testing. For confidence intervals, what do? We just have to use our sample mean as our best estimate, our point estimate of the population mean. So we apply those same principles that we've seen already. But we're not there yet. Sigma, well, if I had the population standard deviation, then great, I have the whole population. So I could just find the mean instead of, well, I wonder what it is, right? And so it gets kind of weird, but so instead what we do is we use the sample standard deviation as an estimate of the population standard deviation. So we use S, which is the sample standard deviation, as an estimate. So we're going to come back to these things, right? What are we going to use in place of mu if I'm trying to figure out what mu is? And what do I use for my standard error? Well, we're going to use the sample standard deviation over the square root of n. One thing that we'll talk more about later is, well, as I increase my sample size, then my standard error is going to get smaller, right? Meaning my estimate, I'm more confident in my estimate, right? The spread around it is going to get smaller. But before we can talk about that, we'll need to address these pesky conditions. And it gets a little big, but I'm going to steal it from the textbook. If it'll let me. They really used up all the margins here. No wiggle room. Okay. So there's two conditions that we need to check. So up here we said, when we collect a sufficiently large sample, sufficiently large, we're going to need a way to kind of determine what's large enough of n independent observations. So that independence condition is going to haunt us throughout. And so let's deal with the independence condition. The way that we've seen before is just, was this a random sample? If it was a random sample, I'm allowed to assume that these observations are independent of each other, right? That's why I did random sampling. There's also this kind of add-on. If the data come from a random process, which is like rolling a die, flipping a coin, that kind of thing, you can also assume that they're independent. It's going back to that probability chapter that we did. Ugh. Let's get out of there. But in general, nothing has changed from the independence condition. It's just, do you have a random sample? If yes, you can assume you have independent observations. If no, then you have to assume or argue that your observations are independent of each other. Now, the next one is kind of the new one, the normality condition, which is this sufficiently large sample. We're used to seeing that in a success failure type of situation, okay? But for us now, when the sample is small, we also require that the sample observations come from a normally distributed population, right? If I take a random sample from a normal population, I expect this little miniature version to also be roughly normally distributed, right? So if I can argue that, well, I sampled from a normal population, so even though I have a small sample size, I can assume that it's normally distributed or roughly. As we increase the sample size, we can relax this condition a little bit. Okay, and that's where the central limit theorem kind of steps in and says, well, if your sample size is large enough, then it doesn't matter if you sampled from a skewed distribution, for example, right? The distribution of means will still be normal if your sample size is large enough. And like I said, that's another one of those kind of leave it for 240 type of situations. But as a rule of thumb, so what does it mean to be small or large? These things, usually we use 30 as a cutoff. So a sample size of 30, if you have a sample size that's less than 30, but as long as there are no clear outliers, then we can usually assume that it comes from a normal distribution. And so we check for outliers. What are some of the ways we can check for outliers? Well, what we did before was we used the 1.5 IQR rule. We can figure out if there are any outliers. We're going to be a little bit more cool about it, or relaxed about it, I guess. We can check for outliers. There are kind of two main ways. Usually we make a histogram, right? Or the question will give you a histogram. Make a histogram. Does it look approximately normal? Remember, you're checking this condition if the sample size is less than 30. So it's not going to be beautiful or anything. You're just looking for, well, is it roughly symmetric? Are there no clear outliers here? Then you can assume normality. The other option is if you are given the minimum and the maximum values and they're within 2 or 3 standard deviations of the mean, then that's within the normal range, right? And so there's no reason to expect there to be any outliers because you're looking at the smallest and the largest values, right? So given the min and max, check to see if they're within 2 or 3 standard deviations. If they are within plus minus 2 or 3 standard deviations of the mean. And if they are, there's no reason to suspect there are outliers. If they are, there is no reason to suspect outliers.
What you was given the min?
Given the min and the maximum. That's sloppy. So that's if your sample size is less than 30, then you need to do a little bit of work. If your sample size is greater than 30, then as long as you don't suspect there to be any extreme outliers, then we can usually just say, well, the sample size is larger than 30, so I'm going to assume normality is satisfied. No? Once we've checked these conditions, right, was my sample randomly sampled? If I have a sample size less than 30, are there any clear outliers? If no, I can assume normality. If my sample size is larger than 30, I can just go ahead and assume normality. Yeah. But once these conditions are checked, X bar will follow a t distribution. With n-1 degrees of freedom. Kind of a cute backstory on the t distribution. Of course, it was way back when, but it's called the student's t distribution. And I screwed it up this morning because I said it was Gauss. It was not. It was Gosset, who's the student behind the t distribution. So I don't know if you've heard the story, but he worked for Guinness, the brewery, and he was their analyst way back when. And he kind of developed this T distribution depending on the degrees of freedom, right, for sampling. And he wanted to analyze the mean, I don't know what, but probably alcohol content or something like that, presumably. Right, and so he had to develop this distribution, and then he went to publish, and Guinness said, there's no way you can put our name in this. You can't tell them that this is from our brewery. All the other breweries are going to steal it. And so he published under just student, and so that's why it's the student's T distribution. But now we all know the story, so. All right, so. All right, so the T distribution is how we're going to find probabilities, right? Areas under the curve. I'll put it on a fresh page here. I'm going to say we could find probabilities or critical values using the T table. I have printed copies of the T table. Oh, and I also have your written work if you wanted to have it. I've scanned it, so I don't need it anymore, but save that for later. So we could find probabilities or critical values using the T table. Or what I'm going to do is for precise p-values, we can use the probability calculator. For precise p-values, we can use the probability calculator. So just to get us started on this probability calculator, I just wanted to steal an example, and you can work through the rest on your own. But we want to find what proportion, so what's the area of the T distribution with 18 degrees of freedom that falls below negative 2.10. So I'm going to go to this calculator. In the distribution tab, there is the student option. The student option asks me for the degrees of freedom, which we were told was 18. And I want to find the area below some value. So this option that's here is okay, but I want to click around until I get here. And the one I want to change is the actual T value. So I want to do negative 2.10. And I'm too scared to click it because I think it's going to drop down. So I've got 18 degrees of freedom, which I put in here. And my T is here. And falls below is this option here. Let's see if I can, there. And then here, the student is the student's T distribution. I managed to really bungle it. or make a mess rather, there. Yeah. So then the area in the tail or the area below is 0.025. So this is, so the area below T, and usually we write the degrees of freedom as a subscript. T18 is equal to negative 2.10. If we wanted to visualize it, the T distribution looks like the Z, so you can draw it the same way, but we have T18 is negative 2.10. And we were told, let's use the same color, that this is 0.025. I'm all out of time, but this matches the T table. Which I'm actually just going to steal from here. Shameless. Okay. 18 degrees of freedom. I was able to find, so these are T values now in the T table. We're not going to use it, so I'm not going to focus too much on it. But the one-sided P value is the area in one of the tails, which matches the probability calculator. So Thursday, confidence intervals, hypothesis testing for one sample means. If you have any questions, let me know. Otherwise, I'll see you then.
Can you scroll slightly on the notes?
Yes, let me just stop this recording.